This is lesson 12.1, Visual Displays of Data, ICM. Okay, our basic concepts that we're going to do are these are frequency distributions, grouped frequency distributions, stem and leaf displays, bar graphs, circle graphs, and line graphs. Okay, so a little bit of vocabulary here. You can read this. A population includes all of the items of interest, and a sample includes just some of them. For example, if we wanted to find out how many people who are registered voters support a particular candidate, say Bernie Sanders, let's say, and we would not necessarily be able to take a poll of every person in the population. We would take just a sample, and so there might be 1,000 voters that are asked about that question, and a sample is just a portion of the population. For it to be a good sample, it should be representative of the population. In other words, made up of groups that are reflected in the population in the same proportion. Okay, so the study of statistics can be divided into two main areas. We are going to be principally looking at descriptive statistics in our intro to math, college math class right now. But when you take statistics either in here as AP statistics or in college, you'll also be doing inferential statistics, which has to do with taking the information that we've collected, organized, and summarized about our sample and being able to draw conclusions about that, about the population based on the information from the samples. Okay. So we have raw data, and the raw data that we collect is divided into two different areas. Quantitative, which has the key word in there is like quantity, that's numerical, or qualitative, which is non-numerical and often called categorical data. I like that word because it's so easy to confuse quantitative and qualitative. But let's talk about something being numerical. Just because it is made up of numbers does not mean that it is numerical. It has to make sense to take a sum of it or to take an average. For instance, if I was looking for the average height in my class, I could add up all the heights and then divide it by the number of students. However, it doesn't even make sense to talk about the average phone number or the average number on your football jersey. I mean, those things have no significance at all. So they would not be quantitative. Those two things, like phone numbers, numbers on football jerseys, social security numbers, although they're numbers, they're actually categorical or qualitative data. So you might look to see, does taking an average make sense? Okay, so when a data set includes many repeated items, it can be organized into a frequency distribution or relative frequency distribution, and I will illustrate that on a later slide. For instance, here, the 10 students in a math class were polled as to the number of siblings in their individual families. Construct a frequency distribution and a relative frequency distribution for the responses below. So what I would do is I would list the numbers that I have, 1, 2, 3, 4, and they are my x's. Then the frequency is how often do they happen. So I have 1, 1. I have 1, 2, 3 twos. I have 1, 2, 3, 4 threes. And I have 2 fours. So the frequency tells me how often the individual data points are. The relative frequency is what percentage of the whole are they. So I would just I would add up the frequency. This sums up to 10. And I would take each of these numbers divided by 10 to get my relative frequency. And they are often looked at as a decimal or a percent. So what this is telling me in this class of 10 students, 20% of the students have 4 siblings. And you can see a much neater example of what we just did right there. Okay, so the data from the previous diagram can be interpreted with the aid of a histogram. So all I've done here is I said, oh look, I had 1 1, I had 3 2s, I had 4 3s, and I had 2 4s. So I organized this data into a series of rectangles. In the middle of each rectangle was the number that I put. Notice that each of these rectangles have the same width. That is actually very important. Otherwise, it actually becomes a fraudulent graph. So they're the same width, and it's just a picture, a very visual example of what our frequency did. If this was relative frequency right here, if this was instead of frequency, relative frequency, we could also do the graph. We would label that y-axis with the percents, and it would have the exact same shape. Okay, now we can also convey this with a relative frequency polygon. So if I go back here and if I take the center of each of these and connect it with a straight line and then to the end, that is exactly my frequency polygon. Now if I don't have these two little endpoints here, I have a slightly different graph, and it is called a line graph. But we can reconstruct it the same way. I'm going to go right to the end and show you a different type of line graph. I'll come back and do all of this stuff in a moment, but I do want to show you a different line graph, and that has to do with time. Okay, so often this graph below shows the stock price of a company over a 6-month span. So we often put time most often on the x-axis, and of course that's pretty easy to read. So for instance, in March, we see that the stock price was $7, and we use line graphs often to look for trends and to show changes over time. But it is also a type of line graph. So I wanted to show you that. Okay, let's go back to where we were before. Okay, so we have a frequency distribution here. We're going to talk about a frequency distribution and how that is done. And I'm going to look at this as a dual page display for a moment. Okay, so right here, I have 20 students selected randomly, and they were asked to estimate the number of hours that they had spent studying in the past week. And here's the data that we have. Now, there's really too much data here to to list everything. I think the lowest number here is 15, so I don't want to do 15, 16, 17, 8. Okay, I actually want to group them into some type of logical group. So I've grouped them into the hours 10 to 19 hours, 20 to 29 hours, and so forth. My largest number here was 58, and so um, I have 50 to 59, and I could stop. Notice I don't even have a group of 0 through 9. The frequency there would be 0. I could have, but I did not. And um, so I then just tally up. I look and I go, oh, 10 to 19. So I'll look up, here's 1. Um, Oh, that's the only one. Okay, so then 20 to 29. So I have 1, 2, 3, 4, 5, and that's it. So um, I've just tallied up the frequencies and then, excuse me, and then I have added, and then for each one of those, um, that's how many I have in each group. Now, if I add up each of these frequencies, if I add up the total, so I have 11, 14, 19, 20, okay, and how do I get the relative frequencies? The first box is 1 divided by 20, the second box is 5 divided by 20, the next box is 3 divided by 20, and so on and so forth to get the correct percentages. So those are my frequency distributions. Okay, now there are a few things that you have to remember if you're going to do a frequency distribution chart. Okay, and right here, let me move this out of the way so you can see. Right here, I want to be sure that I obey each of these 4 rules. I make sure that each data item will fit into one and only one class. Okay, so I don't have something that is like 0 to 10 and then 10 to 20, because in which class would I put that 10? So I want to do 0 to 9 and then 10 through 19 so that nothing fits into more than one class. I want to make all the classes the same width. And I want to make sure that the classes do not overlap. Rule 3 and Rule 1 are just about the same. And I want to use from 5 to 12 classes. If I use less than 5 classes, my histogram is not going to give me too much information. If I do more than 12 classes, it becomes difficult to read. It's just a lot of bars and it seems it's going to be very confusing. There is no rule about how many you should use exactly, so that's going to be up to you. And what we want is when we graph these, okay, we want to be able to look at that and interpret the results really well just by looking at the graph. So again, there's no strict rule. Could I have done other ones? Yeah, but just do categories, or we don't call them categories. Just do the groups at the bottom on the x-axis being pretty logical. Um, by the way, there's no rule that you have to have it shaped this way. You could flip where the hours are and where the frequency is and have the bars go horizontally. I'd recommend that for your work here, you actually use graph paper and do it this way, but you might see it on a standardized test or in the news or any place you might see a histogram with the bar graphs going it's not a bar graph with the bars going horizontally. Same deal. Okay, um, so these just a little bit of vocabulary here. Okay, the frequency distributions in the table, you have on the right side was the upper limit, upper class limit, and then the lower class limit. So if it was 10 to 19, 10 would be the lower class limit, and 19 would be the upper class limit. And then, of course, the width uh, is the difference between those two. And the width should be the same. Okay, stem and leaf. Okay, this is so the 10, the 10 digits to the left, I'm just going to read this. The 10 digits to the left of the vertical line are the stems, while the corresponding ones digits are the leaves. The stem and leaf conveys the impressions that a histogram would without a drawing. It also preserves the exact data values. Let me show you how to do this. Okay, I'm actually going to cover this for a moment, and I will, oops, that's not what I wanted to do. I want to draw a rectangle. That's not good. I'm going to draw a rectangle here, and then uh, um, cover it so you can and construct it with you. So I want, okay, so let's do a stem and leaf plot. Okay, so I can look here and I could see my lowest number is 15. I could start with a 0, but I'm going to start with a 1 and then just count up. These are the 10s, 20s, 30s, 40s, and 50s. Okay, and these numbers here are my stems. Okay, so then I just look at each data. So for 15, that's here. 58 goes here. 37 goes here. 42 goes here. 20 goes here. 27 goes here. 36 goes here. 57 goes here. 29 is here. Oh, I have another 42. That's here. 51, 28, 46, 29, 58, 55, 43, 40, 40, 56, and 36. Okay, so that's how I record it. Note, I do not put commas in between these. I don't put commas. This is my stem. I actually could get my raw data here. I have the number 42. I have another 42. I have the number 46, 43. And I can interpret this where I just take any one of these and I'd say that that equals 15. So that is a stem and leaf display. Now, these leaves right here, it's nice if they were in, if sorted in numerical value. So I'm just going to get rid of what I just did and show you the nice, neat, completed one where they have sorted all of those numbers and they have taken each row and put it in numerical value. And that is your stem and leaf display. A frequency distribution of non-numerical or categorical data is in the form of a bar graph. It looks very much like a histogram. A bar graph is given for the occurrence of vowels in this sentence. And notice that there is a space between each of these bars. That is typical. I know you've been doing bar graphs even in elementary school, so that's okay, now a graphical alternative to the bar graph. We use bar graphs only for categorical or qualitative data. We use circle graphs only for categorical or qualitative data. And that is, a circle graph is also called a pie chart. And you've been doing those for a long time. Each of those percentages represents the relative frequency. Okay, so we can see from here that Amy's monthly expenses, 25% of her monthly expenses was rent. And that is, how do you get the angle? You would take the percent of 360. So 25% of 360 is 90%. Okay, and you don't have to use a protractor in this class. Certainly you can if you wanted to be very exact, but otherwise a good estimate will be sufficient. Okay, and we talked about this already, and that's the lesson. So if you have any questions, please come and see me. Thank you.